Welcome to the 8th Science Industry Roundtable organized by EuLA, the European Lime Association. The topic of this roundtable is Masonry and Eurocode 6, aiming at preparing ourselves to the discussions of the national annexes of these standards. The cycle is organized in 3 parts and 5 online sessions. In the introduction session on December 3rd, we had presentations and a panel discussion on the future of Masonry. Today, we start the cycle of 3 thematic sessions. Today's special session 1 is on Mortar Masonry Bond. Special session 2 is on the impact of formulation and is now fixed to take place on February 17th. A 3rd special session will be on execution and quality control. It is now clear that the final discussion of national annexes in March has to take place virtually, and the date is still to be defined. The moderator of today's special session of Masonry Mortar Bond is Professor Paolo Lourenço from the Minho University. I now give the floor to him.
Okay, so good morning to all of you. Thank you very much for attending the session and for the streaming vision. It's a pleasure for me to be here with the 3 distinguished guests. So the first one that will be presenting is Paul Dupont Christiansen. I know him for a very long time. He has been working, he worked in the Danish Technological Institute for 25 years, related with Masonry. He was involved in the, I think, very interesting project, ecdesign.com, which is online software that many people use for Masonry design. He's extremely experienced. He has been involved in code drafting, also in the PT team responsible for the supervision of Masonry, part 1. The second speaker is a very good friend for a long time. It's Dr. Rob van der Plaum. We did the PhD more or less at the same time while he was working at TNO, the Research Institute in the Netherlands. He, I think, has been also the International Product Manager in Wienerberger for a long time, 20 years or so, working there. And so he's also extremely experienced, not only the topic of bond, but also in the market and product development. So it's, I think, very exciting to have him here also. And the third speaker is Dr. Miguel Azenha. So he's working at University of Minho together with me. And we were jointly supervisors of Mira Ramesh, which hopefully will become a doctor in a couple of months, in a project that was funded by the European Lime Association. So basically, we'll be presenting the work of Mira, which I think it will be nice to complement the general presentations of the other speakers. And that's said, so thank you again for being present. I would invite you again to put your questions in the YouTube streaming channel so that we can answer live. Anytime during the presentations, we will start the discussion afterwards. And so I invite Paul to start his presentation. Thank you very much again.
Thank you. I will share my screen. Okay, I hope you can all see it. I have the honor of being the first presenter in this topic, adhesion. Okay, so the first thing, why is adhesion relevant in the modern architecture? Because in the old days where we had other kind of constructions with heavy roof, heavy wall, heavy slabs, and very thick walls, wind problem and so on wasn't that big issue, wasn't that big a problem. But nowadays we have, in many construction, very light roof, we have thin walls, and suddenly the wind load has become critical. And the only thing to gain load capacity is actually the flexural strings. The flexural strings is more or less relevant, is more or less connected to the adhesion. The adhesion has influence on several parameters of strings. That is the two flexural strings, Fxk1 and Fxk2, and the initial shear strength. And if there's no adhesion, then there's no parameters of strings. The value is 0, and then there's a problem to get the load capacity. We have it in beams also. The shear stresses should be more than 0, should be a high value, otherwise we can't get the lintels, the beams, to have any load capacity. And for the new constructions, the transparent masonry, the flexural strings is also important, because in many cases there are no support behind the transparent masonry. So there, in the very small overlap, there should be flexural strings too. Let's go through the parameters where adhesion has the influence to see how they actually work. We have Fxk1, bending strings parallel to horizontal joints. This consists actually of two types of parameters. We have the failure in the units, that is especially when we have weaker units, and then we have the failure in the mortar. That is two different failures. We can have failures in the mortar, that is this line here, and failures in the unit, that is this line here. Failures in the unit is of course not anything to do with adhesion, but it influence on Fxk1, so it's important to know the difference between the two. Anyway, when we have to calculate Fxk1, this is of course the minor value of the flexural strings in the unit and the flexural strings in the mortar, in the joint. In our national annex, we have introduced a new parameter, that is the flexural strength in the mortar, that is Fmxk1. And that is actually the difficult parameter to determine, and that is actually the adhesion. We'll come to that later, but to see how Fxk1 is determined in our national annex, we have this table here. And there we have the flexural strings in the unit. It goes like this and this. And the flexural strength in the unit, it goes like this up here, and that is connected to FB. So if we have a combination, for example, 0.3, that is the flexural strength in the unit, and we use that in combination with a stronger and stronger unit. So we have this 0.3 flexural strength in the joint, and we use that mortar in combination with a unit where the FB is getting stronger and stronger. Then we'll go from a failure in the unit, and we go to a failure solely in the joint. So Fxk1 is increasing. And we use that table in our country. This is a part of our national annex. It's a little complicated, but once you get used to it, it's quite easy. The determination of Fmxk1, that is the adhesion, the flexural strengths in the mortar. We have made a lot of tests using lime cement mortar, lime cement 50-50, 700, lime cement 35, 65, 60, 650. And we get this curve we have here, where we have the one with the small amount of cement here, and the curve for the mortar with a large amount of cement here, and of course it is a little higher. and it is very connected to the initial suction rate. If you have a high suction rate, you get a low value for the flexural strength in the mortar. If you have a low value for the suction rate, you get a high value for the flexural strengths in the mortar. So the point is, what we found out, that when we have these dry mortars, they contained in the bucket 15 to 18% of water, and the optimum suction rate is below 2 kilogram per square meters. If there is a higher suction rate, it will actually dry out the mortar. We measured how much of the water actually was transported to the unit during the bricklaying, and that was 2/3 of the water it goes to the unit. So in general, we found out that there is a general shortage of water when we are doing the bricklaying. And of course, this problem can be reduced by pre-watering. And that, when we calculate it, it is more or less like going from 4 to 2. It is reducing the suction rate a factor 2 when we do the pre-watering. So for example, if we go from 4, we get this flexural strength in the mortar, and we go to 2 and we get this flexural strength in the mortar. And that can be seen on the test, provided we have a strong unit, so the failure is not going into the unit. So this is actually the curve that we use when we are using these two mortars. The curves are only valid for natural air content, 3 to 4% or something like that. In many cases, some producers use additive that is increasing the air content, and that will reduce the adhesion eventually to 0 when there's enough air in the mortar. So this is a fast determination of FXK1 on site. It's not that difficult to measure. If you are in doubt on site, you just make a specimen of two units and a mortar joint, and then 4 screw clamps, and then a bucket of water, and then fill it. And then when it breaks, you can measure the amount of water and finding FXK1. That's very easy. And here you can see a failure, a fracture, that actually shows that you have some failure in the mortar and some failure in the unit, a large failure in the unit. So it's difficult to make this mortar stronger when it comes to adhesion, because the failure is more or less in the unit. So this is a good mortar. Okay, FXK2, that is more or less same procedure. You have 2 yield lines. You have 2 failure. The one failure when it comes to FXK2, that is bending on a vertical line, that is through the units, or it is solely in the joints, the 2 failures. These failures consist of 2 mechanisms, of more mechanism, but it contains of several mechanisms. If we look into this failure through the units, we have, of course, the bending strength from the units. We have flexural strengths in the head joints, and we have the flexural in the bed joints here. So the capacity comes from 3 things when it comes to failure through the units. When you have the failure solely through the joints, the capacity comes from several other points. That is torsion in the bed joints, that is shear in the head joints when the failure is coming, and it is flexural in the head joints. And of course also there is the bed joint itself that has some bending capacity. So we assumed that there were this correlation. The unit, the flexural strength of the unit itself, must somehow be proportional to FB in a power something with a different correlations to it. And we have the torsion that is an adhesion problem, so that is relevant to FXK1, and the head joint that is also proportional to FXK1, and the FVK0 is also proportional to FXK1. And the bed joint itself must also must also be proportional to FM, the bending of the 3 bed joints. So this correlation were assumed, and then we we made 100 tests estimated according to the standardized test, to determine the constant and make some regression analysis, and it fit very nice, I must say. And we made this expression that is shown here, that fxk2 can be expressed as fb in the power of a half, and a proportional constant to the mortar strength and to the fxk1. And similar for the failure in the joints only, we have the same value here for the bending of the joints, and we have this proportional constant to fxk1. So if we use this formula, we got a very good prediction for fxk2. And here we have the table that we normally use. So we go in with, for example, fxk1 that represent the adhesion, and then we put in the units fb. And we can see if we go with a very weak unit, we have a failure through the units, and then the units is getting stronger and stronger, and then the failure will be solely in the joints. And then we get the same value whether we put in a higher strength unit, because the failure is only in the joints, and that can be seen in this line here. So this is the system. This is the two kind of failure that is put into the table we have here. The initial shear strength, we made some tests. That was the easy part. It always showed that FVK0 was larger than or equal to FXK1. So in our national annex, it is given that FVK0 is equal to FXK1. So the conclusion we made was that the mechanism in the previous table, then it is possible to determine all three parameters related to adhesion, that is FXK1, FXK2, and FVK0, only from one parameter, only from one adhesion parameter, and that is FM XK1, F mortar, and then of course FB and FM, but they are normally known. So what we do when we need these adhesion parameters, that is, we are determine FM mortar XK1, and if it is from these two mortars, we use this graph, and in other mortars, we use the normal test EN 1052.5, part 5, in combination with the actual units that we are going to use. And then we get a very good prediction for the adhesion parameters. Yes, thank you. Hope you could see everything and understood everything. And then I will give the word to the next speaker.
Okay, thank you very much, Paul. It was very interesting. I confess I will have queries on some of your slides, but we'll leave this for the panel discussion. And so I would invite Rob to start his presentation now. Thank you.
Thank you.
Okay, thank you, Paulo, for your kind introduction. Good morning, everybody who is watching. I will start sharing my screen. Share. And then I have to go to full screen, which seems to... Yes, this is funny. This is live. Huh? Okay, now I'm there, I think. I hope you can see my screen now. Sorry, I was not at the first slide. Okay, in follow-up of what the interesting presentation of Paul. Flexural strength, bond strength is indeed, just as Paul explained, expressed in two parameters, FXK1, that's directly connected to bond strength, and the initial shear strength, FVKO, is also directly connected with bond strength. FXK2, as Paul also explains, is also connected to the strength of the brick, the flexural strength of the brick, and I will not go into that. As we know, in the Eurocode, the values for those two types of strengths are given in very simple tables depending on the masonry unit type and its strengths and the mortar strengths. And it is also said that for mortar, they are only valid for mortars without admixtures, and that is a little bit funny because, as we know, all the factory-made mortars contain admixtures. But anyway, that it will be corrected in the next generation of the Eurocodes, where we this exemption is only mentioned for on-site made mortars. When we look to, for example, the table of the initial shear strengths as it is now, we can see that I don't know if you can see my cursor. Yes, for clay units there is a distinction made between the mortar strengths, and based on the mortar strengths you can find for general purpose mortars flexural shear strengths, and also for thin layer mortars and for lightweight mortars, and just for all the other type of units also. The same table we can find more or less for the flexural strengths, but what is funny is that, for example, for clay we now see only a distinction between two mortar strengths, smaller than 5 and bigger than 5, but as Paul already indicated, the initial shear strengths and the flexural strengths FXK1 are very much correlated to each other, and so you can wonder why this table is not the same as the table for the shear strengths. And what is also a little bit of funny in the Eurocode is that the table for the shear strengths is part of the normalized text, but the table for the flexural strengths is not part of the normalized order of the text, but an NDP and in a note, and that's mainly because some countries really don't want to recognize the FXK1, but of course they need the FVKO, the initial shear strengths in their design. But anyway, that is what it is for the time, but you can wonder if it is that simple. If we look, for example, to this literature reference from Root, published in the Masonry Society Journal in 1995, you see a huge amount of tests where on the horizontal axis we have the mortar strengths, and on the vertical axis we have the mean flexural strengths he measured from different series. And there you see a huge scatter, and you see a very low correlation factor. So perhaps it is not that simple, the correlation between mortar strengths and flexural strengths, bond strengths. Another literature reference from Schubert from 1988, where he explains what kind of parameters influence the compressive strength of the mortar in the joint. Okay, this is the compressive strength of the mortar, but you can imagine that a lot of those parameters also affect the bond strength. And there we see the mortar composition, aggregates, admixtures, the water content, etc. And from the brick type, the water suction, that was also already mentioned by Paul. So it is not that simple, bond strength. It's depending on many, many parameters. Here, so you have a list, for example, the mortar composition, the sand has an influence, the grading of the sands, even the shapes of the sand grains have an influence. You can find a dozen literatures on that. Of course, the type of binder we use, the cement, the lime, in old times we also used a lot of pozzolanic materials. fines that can be added to the mortar, for example, grinded limestone, the amount of water, the binder sand ratio, the water binder ratio, the additives, all that play a role to obtain a certain bond strength. If you look to the brick, of course, the type of brick plays an important role. The pore size and distribution in the brick, that determines again how the brick is the suction of the brick, not just a rate, but also the behavior in time. The surface roughness plays an important role. Bond is not really a thing that where there is a chemical connection between the mortar and the brick, but it is a mechanical connection where the cement, hardening cement or other hardeners grow into the pores, into the surface of the brick and in forming a connection in that way. Maybe the only exception might be concrete units where you can expect a chemical connection between a cementous mortar and the connection and the concrete. Of course, the water absorption, the suction rate plays an enormous, big role. And also execution, what kind of temperature do we have at the time of execution? What is the relative humidity plays a role? How good are the joints filled, the workmanship, the curing afterwards? Is it done anyway? All those factors play a role. And at the moment, the mortar and the brick comes together. During the bricklaying, you have a certain amount of water in the mortar. The brick starts to suck out the water out of the mortar. So the water cement ratio can become too small, as Paul already said. But to avoid those kind of things, you also need a water retention capacity of the mortar, especially if you have high suction rate bricks. So it already means that when you have a brick, a certain brick, you cannot say, oh, I need a mortar with certain strength class. No, you need a mortar with a specific properties that can cope with the type of brick that it is used with. Of course, taking all those factors into account every time is not very easy or not an easy way to make a design calculation with the Eurocode. So simple relations are needed in coders for day-to-day design. And to cope with all those different aspects, the National Annex will continue to play an important role to reflect the local experience and possibilities we have. And I think Paul showed a perfect example of that. And it's funny to say that that was not my intention, that he said that the Danish National Annex assumes a one-to-one relation between the initial shear strengths and the FXK1. And I think Denmark and the Netherlands are on one line, because in the Netherlands, Dutch National Annex, that's also the case. I think that's one aspect, calculating with a bond strength, a flexural strength in design. In the work, you need also be able to obtain that bond strength. So I think for serious work, the required bond strength should be specified in the design brief. When you should select a mortar really based on experience with and knowledge of the bricks you are using in that project. I know for really serious projects, for high-rise projects in the Netherlands, in most of the cases when it comes to facing brick masonry, the bricks are sent to the mortar company that is contracted to really test out if the mortar that they want to use is working and get the desired level of bond strength. Of course, those cases to have repeatability and consistency of work, factory-made mortars are preferred. And what is the Dutch way to really make sure that the bond strength is achieved? We have made the constructor responsible to achieve the specified strengths. So in the end, when there is a problem, he is the one who shall correct it, and he is the one that should hire a masonry crew or a subcontractor with real workmanship to achieve the good bond strengths that is needed for the project at hand. For the future, I think there is a huge, we need performance-based mortars. Oh, I touched my the wrong button. I think we need performance-based mortars both for the compression strengths and for bond strengths, and it will be a challenge for the mortar producers how multifunctional they can make a mortar with regard to the broad variety of bricks that are available on the market. Do they need 10 different mortars, or can they cope with 3 mortars for all the bricks or whatever? I don't know. I think it's not that easy just to state the mortar compressive strength. That is not enough to achieve a good bond strength in practice. Okay, that is it for me at the moment. So I will stop sharing my screen and hand over to Miguel. Please, Miguel, the floor is to you.
Okay. May I start, Mr. Chairman, Paulo? Yeah. Okay. Thank you very much. So I'll start by sharing the usual screen and putting in presentation mode. So good morning. I'm really happy to be here present in this roundtable. I'm sorry, I'm still just finishing my setup. Yeah. So I'm here to present the work that was carried out by Lourenço, who is a PhD student at the University of Minho, just finishing. So he's just polishing the last things on the chapters of the thesis. And it was a work supervised by me and Lourenço here at this roundtable. And it's what I'm about to present is actually a short part of her work, which was related to the impact of lime in mortars on bond strength of unreinforced masonry. So the program was much wider, and it focused initially on the composition of mortars and the influence of the lime in the behavior of the mortar itself. And then we selected 3 mortars, and we went deeper into several characteristics of masonry specimens. And one of the things that we studied was bond strength. It is also very important to mention that this was a study made in partnership with the European Association since the beginning, and with a strong support, I would say. So there's the index. I'll be speaking mostly about the flexural strength and shear bond strength, but initially, of course, speak about the objectives of the work and the material properties that we actually use, the mortars and the units. So it's not really necessary to make a really strong introduction. These parameters are important, and Paul and Rob have made a very good reason why they are important. According to Eurocode 6, we need to take into account this FXK1 and FXK0 and FXK2. So nothing serious to say there, because it's been said. And what we did in this round of experiments was to take up a repeatable framework where we could test 3 different mortars with the same unit for these 3 properties: the flexural strength parallel to the bed joints, flexural strength perpendicular to bed joints, and the initial shear strength, sorry. And for that purpose, we selected these 3 mortars that I'm showing now on the screen. These 3 mortars comprise the first one, which is the reference mortar made out of, sorry, I'm just pointing the laser. The first mortar made only of cement and sand, the second mortar made of cement, lime, and sand, and the third one as well. So the 50 is the 50% of lime in the mortar, the 67% of lime in the mortar. So the 2 mortars containing lime were tailored, and also the reference one were tailored with a common framework of getting the flow value within 175 plus minus 10 millimeters. This was the definition of the water content was made by that, so that these were really realistic mortars in terms of their application, and even their composition was strongly based on experience and also on the national annex of the Eurocode 6 that exists all around and give us these types of composition. So they are pretty standard and realistic. On the reference mortar, we wanted to go to something that only contained cement as the binder, but had a reasonably similar compressive strength in the end. It ended up being a little bit higher. As you see, we had 11 megapascal for the reference and 9 for the L50 and 469 for the L67. This was expectable, but in this way, this is our framework of comparison. It is noteworthy also to mention that the lime was a CL90S, and the cement was a cement type 1 42.5 because we wanted to keep it as simple as possible for the chemistry in order to understand how it works. But the representativity, we still considered it to be a nice one. In any case, we also measured other properties, which are shown in the screen for reference, but I will not pinpoint them now. As for the units, we used the solid frog clay bricks, which were molded clay bricks. They were gently supplied by Wienerberger. And of course, we had some basic data provided by the supplier, but we made our own tests, of course, according to standards. And I would just like to raise your attention to the fact that we have a compressive strength of 22 megapascal. So we are clearly on a situation where the compressive strength of the unit is larger than the one of the mortar, which is more than normal. And we have our IRA is a little bit on the high side, so this makes it a little bit more dangerous in terms of getting water from the mortars. But in our preparation of the masonry specimens, we always pre-soaked the bricks in water for 30 minutes to make sure that this aspect would be minimized, but it's still an aspect to consider, of course. So then, going directly to what matters in the presentation, which is preparation and then the results. So for the preparation of specimens, we tried to be as repeatable as possible, and we had a strong focus on keeping processes similar. So we weighted materials very carefully. We kept materials under constant temperature and humidity, well known before the mixing, and this was made in a very systematic manner. The mixing, we did mixing with the procedures you would find in situ in many situations with a bucket and a hand mixer. And then it was actually a professional mason with more than 30 years experience on this that did the actual construction of the masonry with very strict norms imposed by ourselves to do this. So Mr. Manuel was very kind to do this within the time that we had assigned to the process. So it was very important that every mortar was used within 60 minutes of its preparation. So we don't have issues there. And as for the curing, even though we didn't use a climatic chamber, we were on a basement, and this basement was really constant in terms of temperature and humidity that we measured throughout the year, even though the humidity was a little bit on the high side compared to normally what we would find in some laboratories. As for the mixing, we use the N96 for the reference. So for testing, we start by disclosing results for the flexural strength, and we use the standards, of course, EN1052. And as we had three mortars, and we wanted to have some checking of repeatability, we made 3 specimens per mortar, and this resulted in 9 specimens per test. Of course, the tests were 2, so 9 specimens for testing parallel to the bed joints, 9 specimens for testing perpendicular to the bed joints. The setup is here. It was the same for both of them. I don't think I need to go into too many details because this is pretty much standard. The perpendicular to the bed joints test was made in a direction that is not the one of gravity in terms of the self-weight, but this had minor effects. It was calculated in the analytically, but it was not a major effect. And of course, we followed the standard in terms of the calculation of the strength in the of the calculated strength. And of course, the experiment made in displacement control, we had very great care in not imposing any fixation to rotations in the bottom, and of course, the measurement of the deformations with LVDTs on both sides. Going into results and focusing firstly on the top part of the slide, where we see results for parallel to the padding flexural strength, and focus first on the repeatability. So we have 3 specimens per each case, and we see the force displacement diagrams, which are decently coherent with each other. So it's very important when analyzing experimental results that we have faith in what we saw, and we are confident that this is a repeatable process. The results were naturally bigger in terms of calculated stress and strength for the reference and the L50. The L67 was smaller, and this was expected. So this in terms of parallel to the bed joint. In terms of perpendicular results to the bed joint, the same tendency existed. The reference and the L50 had higher values, of course, higher than the ones parallel to the bed joint, and the L67 with a slightly lower result. So taking into account the compressive strength that existed in the mortars, this was sort of expectable. So I remind you that the compressive strength was these ones that we see here. So the 11, 9 and 469, and going to the tables of Eurocode 6 that have already been shown to calculate the expectable FXK1 and FXK2, we would get 0.1 for all the cases and 0.4 for the 2 top cases and 0.2 for the bottom in the L67. So what we got were results that were above the Eurocode. So in some sense, such a very simplified table is inherently conservative, and we confirm this conservativeness. There was some deviation, particularly in the perpendicular strength, but in the parallel strength we were reasonably near, even though there was a single case in L67 where we were under. But one of the things that we were targeting here, and this was one of the hypotheses, let's see if there's a very specific difference in the behavior caused by the presence of Pluijm. And this difference existed, of course, but it was not further than what would be expectable by the difference in compressive strength, to our best opinion at the moment. And also we made the shear bond strength test, which is shown here, and we followed as well the norm EN 1052. According to the norm, we should do 3 perpendicular pre-compression states of stress. So this stress was caused by an horizontal actuator with 2 steel plates. So we made a setup with 3 bricks and the 2 joints. And of course, as we needed 3 specimens per situation, and we had 3 pre-compression levels, and we had 3 mortars. This results in a total of 27 specimens. And of course, the test was with the actuator causing shear in the vertical direction. And we had 1 LVDT in each of the sides of the specimen. So each result that we have is an average of 2 LVDTs that inherently don't give us equal results. So the averaging will cause some artifacts when looking at the results. This is the presentation of the actual result we obtain. So I'm not showing the 27 specimens, only 9 of the specimens. So we are showing 1 specimen per each level of pre-compression. So here we have, for the 3 mortars, 3 example specimens that we obtain. Each one of these lines is actually the average of the 2 LVDTs that we had. So this just frames the magnitude of results that we obtain. Again, relatively similar in terms of the numbers for reference and L50, and slightly lower in L67. So from a qualitative point of view, we are sort of there, and the typical shape was obtained. But when we try to analyze this from the point of view of was this expectable somehow, and then later compare with Eurocode 6, first of all, we could see these results that are shown on the top part in table form, and in the bottom are shown in graphic form. So we are plotting compressive strength of the mortar against the shear stress that was observed. So we can see that there's clearly a tendency of increase as we go towards the reference mortar, which had the bigger compressive strength, and of course the expectable increase with the increased pre-compression was obtained. So here again, there was not something very specific we could say very conclusive that differentiates the line behavior, except for the fact that the impact on strength also had an impact on the results. For the processing of these results to get the cohesion and angle of friction, we follow the procedures that would be followed in normal situations to make the regression of the results for each one of the mortars. So for each one of the types of mortar that we have in the masonry specimens, the regressions are shown here, but they resulted a little bit unexpected, I would say, in terms of, for example, of cohesion, or you can go directly to the FBK0 that was calculated. So we actually have the biggest value in reference, which was expectable, but the difference between the reference and the mortars containing lime was much bigger than initially expected. So because of the fact that in the flexural strength, which is related to this, we have the reference and the L50 pairing together, and then the L67 being lower. And here we get a cohesion that is much similar between L50 and 67, and the reference seems to be higher. And the angle of friction also brought a little bit more of confusion, I would say, because there was a biggest angle of friction in the L50 as opposed to the reference and L67, which was a trend that we were not really expecting to begin with. So, of course, at this point, and we are speaking from a research institution, we looked at this and we wondered, might there be an outlier? And under potential assumption that there might be such an outlier, we thought maybe this is this 1 megapascal shear stress specimens, even though the variability was low, might be outside of might be an outlier. So in that case, we decided to try to compute the shear strength, the angle of friction from all the specimens together. And there was a common calculated angle of friction. And from this common calculated angle of friction, we independently for each mortar tried to calculate the value of FBK0. And when we did that, the trend ended up being more similar to what would have been expected from the flexural strength, with the reference and L50 similar, but with some advantage for the reference, and the L67 being lower than those. And then in relation to Eurocode 6, this also still looks coherent, such as the previous analysis. So for conclusions, and I'm approaching really the end of the presentation. So we wanted to provide a really comparable situation where the single variation between the specimens was the fact that there was a change in the blend of the mortar. So we were using always in the blend of the mortar, particularly the presence of lime, always the same sand, always the same procedures, everything the same with a very big control. We tried to assess the impact of having the lime on the mortar, and it was not so evident. There was not a trend that could be captured that went beyond the capacity of analyzing from the compressive strength. And the Eurocode 6 ended up being a conservative regulation that was actually giving us the correct predictions, meaning they were lower than what we got, except for FXK1 in the L67 mix. And sorry for having extended myself in about 1 minute, and I thank you very much for your attention. Thank you.
Okay, so thank you very much to all presenters. There's a couple of questions that have been set, and maybe I would start with some general comments, and then we could try to go some of the details. So what I could understand as a general conclusion, if I am correct, is that this is a very complex problem, as introduced by all speakers. I had a few queries on Paul's presentation. To be honest, even though I looked into the national annexes, sometimes they are too many and difficult to control. So I was very impressed with the level of sophistication of the Danish national annex. I don't know if this was clear to all. It was not clear to me, so I think it would be good for the viewers to understand. So my understanding is that the test zones were only for clay bricks. This is point 1. My second understanding was I didn't understand very well the mortar compositions because it was lime, hydrated lime, but I understand maybe the second figure was cement. So in the slide where you had the compositions, and also, if I understand well, these were measures in weight. So could you explain a little bit more in detail which are the traditional mortars that are used and that you show the compositions?
Yeah, I'll just share my screen so we can get the PowerPoint back again. Is that okay?
Yeah, yeah.
Then it's easier to see. There. Yeah, we made test with the units were only clay units. Yes. So the initial suction rate is for the normal clay units that we use here in Denmark. And the mortar is a composed lime cement mortar. For example, in kilo, 50 kilos lime, 50 kilo cement, and 700 kilo sand.
Okay.
And the
That's
sand
what I understood, so it's clear.
Yeah. And the sand has, of course, a certain grain curve that it should follow. So it's it has the standard grain curve that they normally have. The lime is hydrated lime powder. I hope that is.
Yeah, it's very
unique.
clear now.
Yeah.
Thank you very much.
Yeah.
So my question, I mean, I don't know if any of the panel members would like to comment also on these results, but my question now would be more generic, also related with the comment of Rob and the comment of Andrew Smith, that he is stating that he really agrees that the future needs to define better what is the right mortar. And so one size does not fit it all, and there's many often problems in applications related to mortar use and to bond deficiencies. But my question is, so both Rob and Paul were making a comment. Paul clearly in the national annex that what is the limit of air contents, and Rob making it clear that the mixtures are not applicable. And so, I mean, to my understanding, in Europe, we're talking about 85 to 90% of dry mix mortars application. And so mortars made on site are of very limited use, in fact, in Europe. And so Rob was telling us in a way that Eurocode 6 is not really applicable to these mortars. And Paul, that also the national annex is not really applicable. I mean, I know I'm exaggerating.
Yeah.
But I would like to have your comment on this link between the code and between the use of mortars in practice. No?
Yeah. So as a starter, Paulo, I did not say that the Eurocode was not applicable, but we made in the Eurocode, the restriction was made for the values in the table that you were not allowed to use admixtures. And that was especially there because there was an old friend of us who unfortunately died at too young, Eric Kier, who pushed that ruling because of the very bad experience with air entrainers in mortars, I think. But I think that the day-to-day practice is that bricklayers do not accept mortars without air entrainers because they would be too heavy to work with. That's one point. But on the other hand, there are much admixtures, plastifiers, etc., that can enhance the bond strength. So it is not just one side. The coin has different sides, and I'm happy that in the next Eurocode generation we have said those tables are valid for, in principle, factory-made mortars, what it should have been in my eyes, and I think we are going to correct that error. So that is one aspect. Maybe Paul can comment on that.
Yeah, our lime cement mortars are for most of them also factory made, and some of them are made on the side for small buildings and so on, but it's easy to get lime cement mortars that are factory made. And then furthermore, I'd like to add that the producers of units in Denmark has agreed to put on a declaration of the initial suction rate, meaning that if you have this and that stone unit, then you know it has a suction rate from 2 to 2.5 or something like that, and that make it very much easier to find the mortar that is good when you combine it, because some producers of mortars say we have a mortar for high initial suction rate and for low initial suction rate, and we have one in the middle. So we do have different mortars for different suction rate, and that has begun to be implemented when you do the design. So that has helped not combining the wrong units with the wrong mortar.
Yeah, that's something I can confirm, Paul. In the Netherlands and in Belgium, we have a distinction between 4 ranges of suction rates, so that the mortar also can be adapted to the brick.
Yeah, I think we have had too many damages and failures with combining the wrong thing, so everybody has an interest in declaring the values. Yes.
Okay, so thank you very much. There is also a question in the chat from Frederick Verhelst. If you can read it, Paul. So he's talking about the use, I mean, you say that use hydrate power. He's talking about that you normally use hot mortars. Can you detail a little bit what lime do you use?
Yeah, it is called hydrated lime powder. That is what they call it when they deliver it from the factory. So that is more or less what I know about that. I don't know what quicklime is and so on.
But it's I mean it's a lime putty, or I mean because if it's a lime putty, normally it has more water in it, so it's already delivered as a paste.
No, it's not delivered as a paste.
It's a powder.
It's a powder because you mix it with cement and then you deliver it on site as a factory delivered. So it is dry, and it doesn't, when you mix it, it doesn't have too much water in it, and that is why when you have a unit with initial suction rate higher than 2.5 or 2, then the capacity, the FXK1 is going down.
Okay.
And you need the lime to increase the water retention of the mortar.
Yeah, and you need the lime to make it easier to do the bricklaying and so on.
Yeah. If you avoid the lime, and then the water retention is not high enough, and the brick immediately sucks out the water, and you cannot correct the position of the brick anymore after a second or 2 or so.
Yeah.
So that's why you need the lime for those bricks.
Yeah, for those mortars, that is pure cement mortars, that is our design mortars. They put in a lot of additives to retain the water, of course. So that is also why they can make design mortars for high suction rate and low suction rate. They can just control the additives.
Okay. So I mean, there was a question also from, I believe, Rob on the shear test. The test presented by Miguel. It can comment, to my understanding, is that we looked into the failure mechanism. This was also my query, and they were very similar. And so there was not an issue on breaking the brick or different failure mechanisms involving the mortar or the interface.
Yeah.
Miguel, maybe you can answer, yeah?
Yeah, that was the case. So the failure mechanism was always the same on the joints. Yeah. Of course, not simultaneously. This is obvious. This is what happens in all these kinds of tests. So
because I saw in the graphs that you had an initial peak and then a little bit going down and then again up again. So
yeah,
I expected that because of the increasing deformation, the middle brick again was yeah, because of the, I guess, the dilatation.
Exactly. Exactly.
Hold in the test. Huh? Yeah.
That was exactly the case. So there was a non-simultaneous failure, and the dilatation effects brings this increase that looks funny, but that's what it is. Yeah.
I would like to make a question to the panel members, and also on the results that Miguel presented. And so, I mean, according to the Mason, which is an expert working on mortars for a long time, he did like more obviously the lime mortar. And so this was his preference. I think, if I remember well, 129 was his preferable mortar from the point of view of use on his practice, no? But we are using, in these tests, we are using a mortar with high suction rate, a brick. But the results don't indicate a very large benefit of the use of lime, which in my view, speculating could be because of two reasons. One reason is that we treated the brick too well. So we did, as Paul said, we did very good saturation, meaning that by doing this, maybe the on-site application of this type of brick with a cement masonry mortar would be a disaster, and we did not find it. Or maybe our cement mortar was also too good because there was good flowability and good workability by the combination of the sand we used and the formulation we used. And so we did use a sand, but which had some additional filler to be sure there was no bleeding and that we had a good quality mortar. So maybe we did the work too well. I would like to ask you two, particularly, I mean, also Miguel, if he wants to further comment on what I said, but why do you think we got comparable results for the three mortars, for this particularly high suction brick?
Yeah, I guess you summed it up well. I completely agree with what you said. So maybe the comparison was not really fair and totally representative of what would be the competing reference mortar. This is something that I believe that we, and in our further plant tests, we are working on that, on going in that direction to understand a more realistic situation of comparison. The inconclusiveness here may have stemmed from that choice to begin with. Yeah.
Yeah, I guess that is for sure the case. If you go to the building site and you see how bricks are treated prior to bricklaying, then if you are lucky, in the morning the bricklayer may have a tube with water and spraying some water over the whole pile of brick, maybe touching the top face bricks, but for sure not all the bricks he is laying. Of course, when you have a high quality bricklayer, he will do it better, but for sure the initial water content of the brick is not that favorable on the building site. I guess that is one big source of problems with masonry bond.
Yeah, especially in the summer. Then you have very much problem if they don't take the stack and put it into a barrel of water. Then sometimes in the summer you can see masonry, you can just take the units from the joints because it has no adhesion at all, because the suction rate is higher in the summer.
Yeah.
Okay, so thank you very much. We have two questions from the chat. One is from Jan Kubica that I would like the panel to answer. And he's asking, or he's commenting, that the triplet shear test is based on small specimens per the European standard. And usually the walls have quite larger dimensions. Mm-hmm. And so he's stating that the scale effect has an impact on the results. and the behavior. And this is not reflected in Eurocode 6. So I would like to hear the panel comments on this.
Yeah.
Yeah. I mean, what should we say on that? I think for just the bond parameter, the test is okay. If you look to what we do in Eurocode 6, especially if you look to shear walls, we have a much lower internal friction in the resistance model I think to reflect that problem. And of course, if you have a huge wall and you apply shear on the top, then the shear stress distribution will not be homogeneous over the length of the joint. So that I think it's more a modeling problem than a scale problem.
I think you have a lot of things where you have the scale effect. You also have it with FXK1 and FXK2. When you take small walls, finding the values and using them in a wall 3 times 6 meters or something like that. But that is usually the situation for all kinds of tests. And that is the function of the safety parameters to take that into effect. We did try a very long wall, I remember, on Technological Institute, and there we find that it was actually only 90% of the effect that we found in the small scale test. So it has, of course, an effect, the scale test, the scale effect, yes.
Yeah, and also if you do flexural bond testing and you have 2 or 4 joints in the middle, in the constant moment area, you can also find already an effect, because the weakest of the 4 will fail, or the weakest of the 2, and then the chance that there is a weak one in the test plays also a role. So that's, I guess, more or less the same effect if you have a large panel.
Yeah.
Mm-hmm. Yeah. I'm less confident on the move on FXK1 on the thickness of the wall, which this is not what's stating here. I mean, the point on multiple joints is obviously clear on the weakest link theory and the fact that the weakest joint will fail. But if you test a wall with a thickness of 100 millimeters or 200, then the bonding strength for the same materials is totally different because of the non-linear part of the response. And so a thicker wall has much lower resistance. And this is physically coherent. It's not in the code. I had a long discussion with Rob with the previous version, I think a couple of decades ago, but now this discussion is abandoned.
Okay, I guess it's not a practical decision. And on the other hand, if you look to the walls that we design in flexure, that are not the load-bearing walls, and those walls are limited in the range of thickness in at least in the usual practice, I guess, in most of the countries. So I guess the national annex should reflect your common wall thickness and adjust the parameter to that what you're used to in your designs. So it's another argument for a national annex.
Okay. We have another question from Andrew Smith, and I would like the panel to comment also. So he's saying that the focus today has been on clay masonry and what the panel thinks about other type of masonry units, especially I-section concrete blocks and I-section natural stone.
I cannot say much about the high-section concrete blocks and natural stone. I've not really experienced with it. The only experience I have was with concrete facing bricks, and for concrete facing bricks, we never had problems in the Netherlands to achieve proper bond. So maybe Paul has some experience, or somebody else.
The only 2 types of masonry we use is clay masonry and AAC masonry, which we use a lot. And there we have this thickness problem because we have these 40 centimeters AAC blocks, and the flexural strength determined in 100 millimeters tests is been used in the 40 centimeters blocks.
Ooh.
So
Okay.
yeah.
And on my side, I can just say also that we are looking into that in the further research that we are conducting. So we are widening the shear tests and many more tests that we are doing. And by comparing the same mortars or same types of mortars together with different units. And one of the units we are now intending to further test is indeed a concrete unit. So even though I cannot answer that now, at least there's a promise research is being done on that with the same methodology.
But Paul, I mean, in Denmark, when you use AAC, do you use the same mortars or do you move to polymer-based mortars?
That is polymer-based mortars. That is design mortars that the AAC producers deliver together with their units. So they deliver everything and they do the test in the lab with the same glue and so on. But I mean, the real problem, I have just been out on a test, taking out some samples from a construction made in reality, and we made the flexural strengths for this, and it was 3 to 10% of the value that were declared, and that was because they didn't put enough glue between the joint. They were very just putting some glue on some joints, and in reality the flexural strength and so on were very, very much lower than found in the lab. So that is a real problem, that we can find values in the lab with 3 decimals and making a lot of tests and everything, but in the reality when they're coming to use it, they don't do it properly.
I think that's a nice way in our national annex that we make the contractor responsible for the result in the end.
Yeah.
Regarding the effect of other units, I have at my time at TNO, I had a lot of experience also with problem cases, for example, with calcium silicate, not because I don't mention it because it's calcium silicate, because the suction rate behavior is so much different, where you have a brick that have a low initial suction rate, but it keeps on the suction keeps on for nearly forever. So it's a really an effect in time, and that's why at least the Dutch calcium silicate industry completely moved to thin layer mortars where they are much more polymer based, and the water retention is enough, and they can really achieve a very good bond strength.
Okay, so I see that you are confirming what also Antonio Caballero Gonzalez wrote in the chat, that it seems like at least in several applications, there will be some move towards specific mortars for specific units.
Already happening, yeah, for sure. Yeah.
Okay, I think we have about 5 minutes for the closing. I don't know if anyone would like to put a couple of questions still in the chat, in the YouTube, but I would have a question on my side, maybe first to Miguel and then to our other panels, which is, so seeing this from the point of view of our current cooperation with the European Lime Association, which is still, let's say, going in another PhD thesis from Carolina Briceño, which is now in the 2nd year, I believe, or close to the 2nd year.
Yeah, starting.
Can Miguel tell a little bit what are our plans? And it would be very helpful to have the input of our panel on suggestions or recommendations on changing the plans, if this makes sense, or adjusting the plan somehow. Take into consideration of this demonstration that both Paul, Rob, and even our Mason said that lime is very good to be in the mortar.
Okay, so thank you. The plans are, roughly speaking, those that I mentioned. So we are widening the types of units that we have to others, particularly with the concrete one. And we are widening the experimentation towards the understanding of the effects of lime in a longer term situation. So one of them is the shrinkage and the creep. And the other one, which is also very important, is the behavior and the restrained shrinkage. So we are going also in that direction, because in cracking that may happen in the joints, this can be by a partial restraint to the free deformation of the actual joint, so the mortar, and it can be either by being restrained to shrink or by being restrained by the expansion of the unit itself. So there are very complex matters that in the fields of masonry didn't have yet too much of a development in terms of study. And in the very ambitious version of this study that we are doing further, we are willing to try even to go into modeling. This is probably not going to be achieved in this particular PhD, but we are setting the basis towards modeling of all these phenomena with a strong focus, not only in seeing the behavior of what's happening experimentally, like I evidenced in my presentation today, but also going into numerical modeling, where we try multi-physics approach to modeling the actual moisture and seeing, for example, the uptake of moisture taken by the unit in regards to the mortar since the early ages up to the longer term. And I would say there are many exciting paths that we can follow. And what we are trying to do with this PhD is to pave the way for a different or slightly more sophisticated inputs into the way of modeling these very local phenomena that are not seen as structural as a whole, but they definitely have an effect on the structure as a whole. So globally speaking, this is it. I try to be general and not particularized in any aspect. Thank you.
Yeah.
Yeah.
Yeah. As I think I illustrated in my presentation, there are so many factors influencing the final result. So it would be a great step if you can improve the modeling a little bit to understand all the phenomena better. And I, for example, remember the work of a Dutch guy, Casper Groot, who investigated the initial water transport when just after bricklaying and the influence on the mortar strengths. And I think there you can already find some good indications about phenomena that plays a role, and maybe it is useful to take that into account in your modeling, what you want to do. And considering, for example, shrinkage, what I have seen in a lot of specimens is that you see that when you have a higher shrinkage, and I don't know exactly due to what, but that especially the boundaries of the masonry are that there is no adhesion in the first centimeters in most of the cases, even if you try to fill the joint perfectly and make academic masonry. So yeah, that is really where the materials have different actions and may cause a problem. So if you have some magic stuff to avoid the shrinkage, and of course there are mortars that avoid the shrinkage, maybe that would be also a direction for developing better mortars in the future. But I guess that was not the question.
I don't know if you have any comment, Paul.
No, I agree with Rob. It is the water transportation that is very important, because when we did our test, we could see just after bricklaying that 2/3 of the water went to the units, and after maybe 10-30 seconds or something like that, then it went back again, so the units lost its weight. That was very interesting. So there is a certain water flow that has very much influence on how much water there is for the mortar to harden. So it is very difficult, yes.
Okay, so thank you very much. We are approaching our time. I would like to leave only two messages which I think they were very important from our panelists today, which reflect in a way two countries' experiences with masonry and addressing also the Eurocode. One from the Netherlands that, from my understanding, for complex jobs, put the responsibility in the contractor, which I think it's very good, because when you have multiple materials and someone executing, sometimes the responsibility of damage is unclear. And so this is, I think, a very important point from the discussion today. Second important point, I think, which was also very good, was the work that was shown in Denmark on really having a very extensive set of testing and reflecting this in a more in-depth code, stressing also the relevance of the national annexes. So again, I thank you all present, all panel for the very interesting discussion. I thank also the European Lime Association for the opportunity to be streaming today, and wish you all the best of the day.
Okay.
Okay.
Thank you.
Thank you.
Thank you all. Bye-bye.
Thank you.
Okay, bye-bye. Thank you.